Hello, everybody. Welcome to this recorded lecture on the heart, chapter 20, part 2. We are going into the physiology, sometimes electrophysiology of the heart, and we'll be ending with the regulation both on the nervous system and on the hormonal side. I hope you had a chance to review the part 1 of this lecture. For some of you who are listening to it, we have that in person. Some of you, you received that in a recorded format. So I'm going to start with the screen sharing of this hyper heart. This animation tells us just where we're going to focus, at least at the beginning, and then we're going to branch out from there. So let me start with this screen sharing, and we'll go from there. And we're going to share this one. So here's this animation, the working heart. In the first lecture on the hearts chapter, we have looked at individual anatomical parts, how they function, both cardiac muscle. We looked at the layers of the heart wall. We looked at the two types of valves and how they are working. So in order to animate a heart like what you see on this animation, you see this changing shape of the cardiac muscle. So we obviously need to rely on cardiac muscle contraction. So in the first part of this lecture, we'll take a look at the cardiac muscle histology, and that will be largely a review. And then we're going to ask the question, just where is the nerve impulse coming from to animate this muscle, to send nerve impulses to these muscles? You don't see any nerves attached to the heart, and that's not an accident. Let me just stop here. Take a look at the atria here. These yellow arrows indicate that a nerve impulse has been delivered. So these cardiac muscle cells of the atria contract. So we'll be looking at the source of those nerve impulses, and we'll be discovering the internal pacemaker of the heart, the conduction system, as we'll be calling it. And after that, we'll be looking at the functioning of each cardiac muscle cell. We'll be looking at the flow of sodium and potassium ions. From there, we're going to branch out to explain the electrocardiogram, where those plotted shapes on a piece of paper on the screen come from. So when you look at this working heart, at this particular stage in the contracting heart, only the atria are contracting. When you look at this green line, we are at the very beginning of the cardiac cycle, this 0.8 second working time of the heart. And so it is important to explain how is it possible that nerve impulses can be delivered to this heart with the atria contracting first, and then by a 150 millisecond delay, the ventricles will be contracting. So the conduction system and its anatomical construction will bring the answer to that. And we'll also take a look at, let me just start. And stop right here. So the ventricles are contracting for a very, very long period of time. Let me see if I can step this forward. So we started around 100 millisecond, and if I can forward this, the ventricles are still contracting. You see this yellow arrow, and you see the change of shape of the ventricles. We're approaching 0.4 0.4 seconds in this cardiac cycle. So the ventricular cardiac muscle need to contract close to 300 milliseconds or 0.3 seconds. That is very unusual. Skeletal muscles contract for about 20, 25 milliseconds. So we will be asking the question, why is the ventricles able to contract such a long period of time? When you look at the amount of blood that's squeezed out of the ventricles, it's clearly beneficial for the workings of the heart. The longer the ventricles contract, the more blood will be pumped out of them. So we need this long period of work from the ventricles. Why is this going to happen? Why is it happening? Will be also part of this lecture. So I might come back to this animation, but let's go to the actual lecture slides here. And this is a review of what you have already seen in chapter 4, way back in AMP1, histology of cardiac muscles. And we learned there that while we have muscle cells that share some properties with skeletal muscles, cardiac muscle cells branch. They have these intercalated discs, which corresponds to desmosomes and also gap junctions. This is the artistic rendition. Here's the illustration of the branching of a cardiac muscle cell. And here's this little squiggly line, indicates the desmosomes. Here are more squiggly lines between neighboring cardiac muscle cells. Excuse me. And so cardiac muscle cells also striated and involuntary, meaning that the consciously working part of our brain that we explored in chapter 16, that part of the brain of the cerebellum that gave signals to the skeletal muscles, they cannot make cardiac muscle work. We'll be looking at nerve impulse flow into the cardiac muscle a little bit later and also towards the end of the lecture. So these are the cells. This is the tissue that is actually contracting and squeezing blood out of the heart from atria into the ventricles and from ventricles into the blood vessels. Where is the nerve impulses? Nerve impulse comes to these cardiac muscle cells. We have this internal pacemaker conduction system. We'll take a look at individual parts. So during the cardiac muscle and heart development, a small portion of cardiac muscle cells change their mind, they differentiate, and they become self-excitable. And this means that spontaneously, every 0.8 seconds, they create a nerve impulse in the middle of the heart. So because this nerve impulse creation is periodic, it's spontaneous, and it goes on 24/7, this is where the name pacemaker comes from. So the conduction system has several parts to it. Here's the anatomical location, and we'll go in order from the creation of a nerve impulse and also the conduction, the spreading of the nerve impulse to the entire heart. So the start for the nerve impulses is the sinoatrial node. This is located in the right atrium, not in the left atrium. As you can see in this illustration, only the right atrium. When this group of cells, pacemaker cells, create a nerve impulse, the nerve impulse is quickly spread throughout the right atrium and also, as you can see, into the left atrium. It means that at the beginning of the cardiac cycle, both atria contract and squeeze blood into the ventricles. At this particular time, the ventricles are relaxed, so they are stretchable, and so the atria moving blood into the ventricles will top off, completely fill the ventricles. So here's the reason for the delay. Nerve impulses, this excitation needs to go into the ventricles through this atrioventricular node. The pacemaker cells are thinner here, and they slow down the propagation of a nerve impulse. And so they introduce a 100 millisecond delay. So from the atrioventricular node, the atrioventricular bundle and the bundle branches, we receive the nerve impulse 100 milliseconds after the atria contracted. When there's no nerve impulse to the ventricles remain relaxed. And again, a complete filling of the ventricles is possible because of this relaxation. Once the nerve impulses are delivered, the last portion of this conduction pathway, called the Purkinje fibers, once the nerve impulses are delivered, the ventricles will contract, and the tricuspid and bicuspid valves will close, and blood will be pumped out from the left ventricle into the aorta and from the right ventricle into the pulmonary trunk, pulmonary artery. So this slide is listing individual names. Sinoatrial node, this is the starter. It is programmed biologically to fire a nerve impulse 100 times per minute. We'll be seeing towards the end of the lecture why our resting heart rate, resting pulse is not 100 per minute, only about 75. But this is the programming of the sinoatrial node. If the sinoatrial node is injured or under attack or has inflammation, somehow incapacitated, the atrioventricular node is going to take over. So whichever portion of the conduction system fires the fastest, that part is in control. So when the sinoatrial node loses control, then atrioventricular node becomes the pacemaker, but fires only 40, 50 times per minute. And if both the sinoatrial node and atrioventricular node are incapacitated, then the ventricles have the capacity to become the pacemaker, but creating only 20, 40 nerve impulses per minute. It means that the pulse of this individual, relying on the ventricles only, the pulse would be 20 to 40, which is not enough for most of us to maintain consciousness. Many issues with the conduction system are corrected with artificial pacemakers, and if you know people with this, this can be a game changer for them because the heart rate is stabilized and the control is taken over from the sinoatrial node, or the sinoatrial node is reprogrammed by artificially created electrical impulses that maintain the normal pacing of the heart. So here's this timing. Again, from a sinoatrial node, the nerve impulses will be forcing the atria to contract, and then the atrioventricular node slows the speed of the nerve impulses and make the ventricles wait 100 milliseconds before they get the nerve impulse. So this is responsible, so the atrioventricular node is responsible for allowing the atria to contract first and ventricles with a 100 millisecond delay. We're going to take a look at what's happening in individual cardiac muscle cells. And here is the question, why a single ventricular cardiac muscle cell can contract for 300 milliseconds when skeletal muscles cannot contract that long with a single nerve impulse. So here's the illustration of what happens from a single cardiac muscle cell's point of view. So the cardiac muscle cells receive a nerve impulse. And inside the cardiac muscle, in the membrane of cardiac muscle cells, sodium channels open. This is classical depolarization. We saw this in the first two chapters, that neurons need to depolarize by allowing sodium ions flowing into the cell. So this is the same thing for the cardiac muscle cell. But then here's this plateau region, very atypical to a neuron or for skeletal muscle. For cardiac muscle, there's a special type of channel, calcium channels, that will open, and calcium channels opening lengthen the depolarization to nearly 300 milliseconds. This long depolarization means that the contraction is also going to be much longer. Connecting your mind depolarization with contraction. Once depolarization ends and potassium channels open to start the repolarization, contraction comes to an end and relaxation starts. So the reason why cardiac muscle cells in the ventricles can contract for 300 milliseconds is because calcium flow into the cells stretches out, lengthens the depolarization all the way to 300 milliseconds. So this is just a text version of what I just explained. Cardiac muscle cells, this is a little sidetracking from the electrical impulses. But if you remember from neurons, to maintain a resting membrane potential, and this is true for skeletal muscles too, we need ATP for those sodium potassium pumps. Of course, cardiac muscle need ATP for the muscle contraction itself. And cardiac muscle cells derive their ATP very similar ways to skeletal muscles. We have the creatine phosphate, we have the mitochondrial ATP production, the aerobic respiration, and we have the anaerobic respiration as well. We don't repeat a detailed study of all that. We covered that in chapter 10 with the skeletal muscles. Here we mentioned just one clinical aspect of the ATP production. And cardiac muscle cells have a creatine kinase that is very different from any other protein in the body. And when cardiac muscle cells are injured, let's say they have oxygen deprivation during a heart attack, and cardiac muscle cells will start leaking and dying eventually. That leakage allows creatine kinase to flow into the blood, and we can detect it in a clinical lab. So if somebody comes to an emergency room saying that I think I'm having a heart attack, a blood test might be administered to that individual, and if creatine kinase levels are high in the blood, that person is indeed having a heart attack, because this is an indication of cardiac muscle injury. If creatine kinase levels are normal in this individual, the perception of heart attack is probably coming from other sources. A direct application of the flow of sodium, potassium ions, and calcium ions create the creation of an electrical field around the working heart. And with the electrocardiograph, we can detect these electrical fields and plot them out in time. And when we do that, we have electrocardiogram. The cardiac cycle, the time period for a single heart contraction and relaxation action is 0.8 seconds. So let's see what happens at zero time interval. This is the time when the sinoatrial node creates a nerve impulse. The first wave we see here is the P wave. because the first cardiac muscle that jumps into action after the sinoatrial nodes nerve impulse is the atria. So the P wave represents ion flows from contracting atria. So P wave represents atrial contraction. From the electrophysiological point of view, this is atrial depolarization. The cells are contracting. In about 100 milliseconds, the nerve impulses go to the to the ventricles, and then the QRS phase represents ventricular contraction. This is also ventricular depolarization. And once the ventricles contract, in about 300 milliseconds, the relaxation or repolarization begins. This is the T wave is linked to opening of the potassium channels. And so the ventricular cardiac muscle cells undergo repolarization. And at the 0.8 second mark, the sinoatrial node creates a new nerve impulse, and this electrocardiogram pattern starts over again. We're not going to look into the clinical application utility of this. A large number of heart disorders, abnormalities can be diagnosed from electrocardiogram, frequently used in clinical practice. Again, we're just going to the basics where the cardiogram is derived from. We're not getting into detailed explanation. If you go into the teachmedicalnews.com blog site, I posted a blog about a year ago about a long QT syndrome. Maybe you can learn about that from there. So I mentioned this term cardiac cycle a few times. The cardiac cycle is the collection of all kinds of action that happens within a single heartbeat. So this lasts for 0.8 seconds. We're going to take a little closer look at these end diastolic, end systolic, and stroke volumes. These will be important to consider when we want to measure the cardiac output, the performance of the heart. So I'm going to go to the cardiac cycle illustration, and we have looked at the electrocardiogram, right? It's way up here. During the first lecture, we looked at the blood flow as it's indicated by these arrows, working of the valves. And here is what's most relevant for probably most of the rest of this lecture is these volume changes in the ventricles. So when you look at the left here, we're talking about volumes only in the ventricles. Here is the beginning of cardiac cycle. Sinoatrial node creates a nerve impulse, and the volume in a ventricle will increase because the atria contracted and shoved blood into the ventricles. When you look at the ventricular contraction phase here, ventricles are contracting and squeezing blood out, so the ventricular volume is decreasing. And then the ventricles will fill up again. Now, when the ventricles reach their full volume, this is the end diastolic volume. This is the maximum volume of the ventricle that we can fill it when the ventricle is relaxed. It's in diastole. The end systolic volume is the lowest volume of blood in the ventricle. At this point, the end systolic volume, end of the contraction, the maximum amount of blood has been squeezed out of the ventricle. And the difference between the fully filled and the maximally emptied ventricle is the stroke volume. This is the volume of blood that goes into the circulation. And this is a good indication of heart's performance. we'll be talking about this a little more detail when we look at regulation of cardiac output, the performance of the heart. Some of the other aspects are illustrated in these slides. I'm not going to explain this again. In the first lecture, we have looked at contraction of individual chambers of the heart, the closure or opening of the valves. That is what's described here. It's good to know blood pressure from left ventricle is 120 millimeter. The blood pressure coming out of the right ventricle is only 30 millimeter, and that's the blood pressure that goes into the pulmonary trunk, pulmonary artery. The stroke volume, the ejected volume is 70 milliliter from both ventricles. We'll say maybe a little more meaningful things about heart sounds. For the lecture point of view, it's important there's this S1 and S2 sounds, and the heart sounds are coming from turbulent blood flow. These blood flow is created next to closing heart valves, so a heart sound indirectly telling us that a heart valve is closing. For the S1 sounds, it's the atrioventricular valve, and for the S2 sound, it's the semilunar set of valves that are closing, and blood flow around them creates the sound. So measuring cardiac output, this is done on a minute-by-minute basis. So when you look at the equation here, cardiac output equals to stroke volume, the volume of blood moved out of the heart with every heartbeat, and the heart rate, the number of heartbeats per minute. So when you multiply these two, stroke volume multiplied by heart rate, you're getting the output from heart in 1 minute time period. Maybe I'm going to come back here for a second. Cardiac output changes dependent on the demand by the body. As you are sitting here, most likely listening to this, your heart rate pulse, right, is about 70, 75. This is a sedentary pulse, sedentary heart rate, and your cardiac output needs to be the minimal that your sedentary condition requires. If you are doing a cardio workout at the gym, or if you go out for a run, or if you're doing any kind of physical labor that requires long-term skeletal muscle contraction, your heart rate is going to go up because your cardiac output needs to go up. Increased cardiac output must provide more oxygen and nutrients to those hardworking skeletal muscles. Increased heart rate is easy to measure. Just check your pulse. What is a little secret of the heart is that stroke volume can also be increased. And so increased stroke volume contributes to the increased cardiac output. So it's not only the heart rate increases, but stroke volume also increases. So here's the story of increasing stroke volume when we have a demand. This is called the Frank-Starling law. And the Frank-Starling law basically says that when we put more blood into the ventricles, both left and right ventricles, will increase their contracting force, and they will squeeze out more volume with each heartbeat. Therefore, the stroke volume is going to increase. So this is a way to increase stroke volume and therefore contribute to increased cardiac output. More blood is coming into the heart. Think about doing a cardio workout. Blood is moving faster into the right ventricle. We are moving a lot of blood from this reservoir into the active circulation, and that increased blood volume will stretch first the right ventricle and then the left ventricle, and increased cardiac output comes out of that increased stroke volume. The other way to increase stroke volume is to increase the hormonal effects on the cardiac muscle cells. The chemical agents that improves contraction force are called inotropic agents. So this is now coming from outside, and you see two hormones, epinephrine, norepinephrine, very typical positive inotropic agents, and they increase calcium flow into the muscle cells, and therefore contraction force will be increasing. So this is another way to increase stroke volume and therefore contribute to an increasing cardiac output. Please ignore this slide. This is a mostly clinically relevant situation. We're not going to deal with afterload. And so we discovered that stroke volume can be regulated, can be increased if you want increased cardiac output. And of course, from experience, you know that when your pulse goes up, your heart rate goes up, your cardiac output also increases. So we have this parasympathetic and sympathetic division of our nervous system that create the nerve impulses to either slow down or increase heart rate. And we also have input from sensory receptors. Let's take a look at this in this illustration. This is the best. So the decision-making center is the cardiovascular center. If we are detecting a danger in the environment, our cerebral cortex, maybe our limbic system, sends nerve impulses to the hypothalamus, and the hypothalamus increases nerve impulses to the cardiovascular system. Whether this is a full flight or flight response, or it's just a moderate change in the environment, a nerve impulse is coming to the cardiovascular center, will be forcing the neurons here to send nerve impulses to the cardiac accelerator nerves. The cardiac accelerator nerves will increase heart rate and increase stroke volume as well. Well, before we go there, let's still talk about how to increase cardiac output. Nerve impulses can come from sensory receptors, proprioceptors indicating that the body is moving, chemoreceptors detect buildup of carbon dioxide, baroreceptors detect a lower than normal blood pressure. Then the cardiovascular center again is instructed to send nerve impulses through the cardiac accelerator nerves, and our cardiac output will increase both through heart rate and increasing stroke volume. If our heart rate is too high and the heart rate needs to normalize, then we have a reduced input from the brain centers and the sensory receptors, and the cardiovascular center will send out increasing nerve impulses through cranial nerve 10, the vagus nerve. This corresponding to a parasympathetic effect, our heart rate is going to decrease. So these are the two ways. Think about cardiac accelerator nerves as bringing a gas pedal effect, stepping on a gas when it comes to cardiac output. Nerve impulses through cranial nerve 10. The vagus nerve corresponds to this braking effect, slowing down the heart rate and therefore slowing down cardiac output. That's interesting thing to notice here, that these nerve impulses and the neurotransmitters are all acting on the sinoatrial node mainly. And so even when we are regulating the heart rate or stroke volume from the outside of the heart, the instructions still need to go through the sinoatrial node, the pacemaker apparatus of the heart. There are chemicals that can also regulate heart rate. We have seen epinephrine, norepinephrine, increasing stroke volume. These two hormones of the sympathetic division can increase heart rate. We could say the opposite about acetylcholine, which reduces heart rate. This is the neurotransmitter from the parasympathetic division. Blood concentration of sodium, potassium, calcium can also influence heart rate. We have seen in the endocrine chapter the detailed regulation of blood calcium levels. And so here's in addition to the blood clotting, this is the second reason why blood calcium levels are regulated, because a changing, increasing, or reducing the calcium levels in the blood can affect the heart rate and therefore the oxygen supply of the entire body. So actually, I'm just going to stop sharing here. So this is the closing to the second lecture on the cardiovascular system, chapter 20, the heart. If you have any questions, please don't hesitate to message me or ask me in person after you see this video. I'm going to close this recording and send it on the way to your class. Have a great rest of the day.